I'm Sadek Drubi. I'm here at Erlang Factory with Simon Peyton-Jones and Joe Armstrong. So can you please tell us about yourself and what you've been busy with lately?
Joe, you can start.
Oh, thank you. Yeah, I'm Joe Armstrong, and I'm at the Erlang Factory. I've just been to a very nice talk where Simon has told us about the birth of Haskell and Erlang and how they sort of went along parallel routes solving the same problems. And, I think we can talk a bit about that, because in your lecture you said things about we tried that and it was an absolute disaster. And we also tried, this making everything parallel. Well,
yes.
We did that as well.
Was it a disaster?
Disaster, yes. And do you know this bit about you deleted all the people's programs? We've done that as well.
Yes, so I'm Simon Peyton-Jones. I work at Microsoft Research in Cambridge at the moment. Previously I was a professor at Glasgow University. And I've been doing functional programming now for 30-odd years, because I got addicted to it when I was at university and never been able to give it up. It's like a drug, but a good drug. So I had Haskell as a programming language evolved because a bunch of different academics were working on lazy functional programming languages around the world. But they were all different languages, and we realized that if we just agreed a common language, then we'd be able to share a lot more work together. So we got together and formed a committee, which wasn't necessarily a very promising way to go about designing an elegant and beautiful language. But actually the committee worked really well because we had enough common goals. And so that was in the very early 90s. And Haskell's come a long way since then. Many languages die fairly quickly after they've been designed. But Haskell has lasted 20 years, as has Erlang.
So Erlang had a different start to Haskell. It started in an industrial environment. It started in the computer science lab at Ericsson. And the original goal was to find a better way of programming. It wasn't actually to make a programming language at all. It was somewhat after the event that we discovered we'd made a programming language. That was kind of accidental.
But you also had a very specific application niche, didn't you?
Yes.
We really were a telecoms
Yes.
company.
So we wanted to just program a small telephone exchange in the best way possible. And we wanted to just steal ideas from different programming languages and sort of put them together and just try them out and see if they worked.
But you knew the application niche, and you knew that concurrency was key, right?
Yes.
Concurrency and robustness.
Well, robustness was key.
So
I think I remember back in the sort of 80s going to conferences and talking about shared memory systems and things, and I always poked up my hand and asked the same question over again. Well, what happens if one of these shared memory things fails? And they would say, well, it all fails. And well, that's what we didn't want. We make products with standard Ericsson products should have a downtime of like 4 minutes per year or something like that, or better than that. So we just don't. Our key problem is failure, handling failure, and right from the early days, we thought, well, the only way to handle failure is no shared memory and no transaction memories or anything that locks things, and that's why we copy everything. That's why we have sophisticated error handling. So here we are back in the 80s, about 1984, 1985, just sort of thinking how we can put these things together. And it was only later that we realised, well, we've made a programming language and better give it a name, and people start using it and so on.
So it never struck me quite as forcefully as this before, but Erlang was born very much out of a demand pull. You had a telephone exchange, you wanted to program it, and so you kind of, a language happened to come out of that.
Yeah.
Whereas Haskell was the exact reverse. We were on a mission from God to explain why laziness was fantastic for the world. So it's very much technology push. We want to explain functional programming, lazy functional programming in particular, through the medium of a language. So it was, you were at this end, and we were at this end.
But in the same point in time, we were doing the same things.
Yeah,
because I remember one of the things we did in Erlang, we first of all, we implemented it in Prolog. And I did that, and then later Robert Eerding came along. And Robert was very into parallel concurrent languages. And so we made one of our first big mistakes, which was announcing what the performance of something will be before you've done it. Have you made that one?
No. We never do that.
So we cross-compiled Erlang to Strand, which was a parallel logic. We implemented a language like that, and we happily told everybody, well, it will be 6 times faster before we'd actually done this. And I don't.
And was it?
No. It was like It didn't work.
Naught times faster.
But the first thing we did, we wrote a little Erlang program, we cross-compiled it to all this parallel stuff, and we had like 3 Erlang processes, and it was as parallel as possible, and suddenly there were 6 million processes in the machine, 6 million threads, and we got far too much parallelism. And that was the same time you said, in your talk, you said, well, you know, we tried to make everything parallel, and there was just far too much parallelism. Well, we did it, the same stuff at the same time.
The other nice remark I remember you making about Robert was that he came to you one day and asked if we make a few small changes in the compiler. then the next line in your paper was, Robert is incapable of making a small change to anything. So he completely rewrote the whole thing.
Oh, there's a comment at the top. Joe first wrote this, and then everything is completely different. Yeah, we used to rewrite each other's code.
Anyway, enough jollity.
So Haskell and Erlang, they have like two distinct models of concurrency, right? Haskell is running through side effect free. Erlang is about messaging, and so can you talk a bit about this in contrast to both models of concurrency?
Well, I suppose Haskell initially wasn't a concurrent language at all. It was a purely functional language, and we had the idea from the beginning that a purely functional language was a good substrate for doing concurrency on. But it turned out to be a lot harder to turn that into reality than I think we really expected. Because we thought, oh, well, if you've got E1 plus E2, then you can evaluate E1 at the same time as E2, and everything will be wonderful, because they can't affect each other because it's pure. But it turned out to be very hard to turn that into actual wall clock speedups on processors, leaving aside all issues of robustness, all that kind of stuff, because you get lots of, if you do that style of concurrency, you get lots of very, very tiny fine-grained processes. And you get no locality, and you get very, very difficult scheduling problems. It's the overheads overwhelm the benefits, in short. So from there we've evolved gently towards giving the programmer some control over that kind of concurrency. So that was the first form of concurrency that Haskell grew, was a kind of controlled form of this implicit level of concurrency. We added other things afterwards that we can talk about later, but that was very different to Erlang's model of concurrency.
Yeah, Erlang started with just this pure process and copying everything. The reason for copying was error handling. So error handling was central. So my view of the world and the view of the world I've always had was a lot of little processes all talking to each other in a sort of global namespace.
Right, but that already was completely alien to Haskell, which is just a functional program that was evaluated.
And then weren't
totally
really
different model.
I mean, in the first incarnation of Erlang was just little black boxes were communicating, copying their message. It's the mailbox model, copy to a mailbox. And what we were doing was relational. We had Prolog processes inside the black boxes. Then
but you
we
saw the light.
Well, we had you're launching a rocket problem because we wanted sort of from a black box perspective. If you send a certain sequence of messages in, you want the same sequence of messages to come out. You want that to be reproducible and deterministic. And Prolog isn't like that. I mean, it backtracks and it has things like that. So it just sort of became more natural to make it functional, and all the. We never made a decision about sort of having types or not having types, so that wasn't an issue. We started with Prolog. Prolog didn't have types, so we got the dynamic type system that Prolog had. The issues we were interested in were limiting errors, propagation of errors, restarting things, restarting bits of the system without taking down the other system, having things which maybe are inconsistent while you're upgrading them. Continuously evolving systems, not systems you stop and recompile. We can't stop our systems and sort of globally check they're consistent and then relaunch them. We incrementally change bits of them. We recognise that they're inconsistent under short time periods, and we live with that. So it's finding ways of living with failure, making systems that work despite the fact they're inconsistent, despite the fact that failures occur. So our error models are very sophisticated. Yeah. So when I see things like Scala, or I see on the net there's this kind of Erlang-like semantics, well, that usually means message boxes and mailboxes and message boxes. It doesn't mean all the error handling.
Yeah,
it doesn't mean the live code upgrade. The live upgrade of code while you're running a system needs a lot of sort of deep plumbing under the counter. It's not easy.
I still think it's amazing you can make that work at all.
Yeah, Phil Wadler saw it. You could have two versions of the same module with all the same names. He didn't believe it was possible until we showed it to him, and he went sort of, oh.
So yeah, you mentioned like some other language got inspired from Erlang and from Haskell, also about concurrency. For example, Scala, they tried to they mimic a big part of Scala of Erlang actors. in the same way that languages like F# and C#, they implement features coming from functional programming, more specifically Haskell. Can you talk a bit about this and how things get implemented in the mainstream or in another languages?
I don't know. I mean, people say, well, what will happen to Erlang? And I have no idea. But there are certain languages which are influential, very influential, but don't get widely used. Like Smalltalk, for example. Smalltalk's the ultimate object-oriented language and has influenced Objective-C and all sorts of languages. And it's, it has this core band of pure Smalltalk programmers who don't believe in anything else. But it wasn't destined to take over the world. So Erlang is probably, I don't know, maybe it's in that category. It influences other languages. But it's not, I think it's sort of, it's in a funny place. It comes from a funny place. It comes from Ericsson. It comes from a telecoms company. And that's really not our main business to make languages. Microsoft's main business is, well, it's not the main business to make languages, but you have the sort of muscle to support a language. So we have languages supported by companies like Microsoft and Sun, Java and C# and things like that. Then you have languages not supported by big companies like Ruby and Perl and things, and they have their own communities. And then you have sort of Erlang's in this kind of in between. It's not in the sense of Microsoft or Sun being supported in a big scale, but it's not living all by itself in an open source community. So it has financial resources to do the compiler and keep the core clean, which is very good. So where it goes from there, I don't know.
So, but nevertheless, there is there's a company that supports it,
yes,
isn't there?
Yeah.
Whereas there isn't for Haskell, curiously. So Microsoft is generously supporting myself and Simon Marlowe, but they're not supporting us to work on Haskell.
Okay.
I'm hired as a researcher, and I happen to work on Haskell.
So very good to change and work on C#.
Well, I mean, in principle, it could. I don't think it's going to anytime soon. And I suppose Microsoft could turn around and tell me, please don't work on Haskell anymore.
like they did with Eric Meyer, right?
Oh, Eric is a whole different ball of wax, right? So Eric works in developer division in Microsoft, and that's much more product focused. But amazingly, Eric has brilliantly found a way to meld ideas from functional programming in quite a product-focused kind of way and build a little research bubble in the developer division that they perceive as being actively valuable to them. So I think that's amazing. Whereas I'm a mere parasite. Right? I'm a researcher who isn't required, on a month-by-month basis in the way that Eric is to produce stuff that's of immediate value to the company. But I think Haskell is also maybe a bit different to Erlang, and I think of Haskell as its principal value is as a kind of ideas factory. Right? It's a laboratory in which ideas can grow and flourish. It has a very active user community and a very active research community. Lots of research papers use Haskell as their substrate, and indeed use GHC, the compiler that Simon and I built, as a substrate for their work. So it's a laboratory in which ideas can go and that may then get transferred elsewhere. So that we've seen lots of examples for that, not perhaps specifically for Haskell, but for functional programming in general, going right back to garbage collection, which is now taken as, well, of course you have garbage collection, but it was a long time before that was taken as read. There were a long time in which that people thought it would never be taken as read, but that grew up in the functional programming community. Generics in Java and C# grew up in the functional programming type system world and are now taken for granted. LINQ, the language integrated query system in C#, is heavily informed by ideas from functional programming. So I'm actually quite happy if Haskell serves as a role of generating ideas that then move into the mainstream. Whether Haskell will itself ever become a truly mainstream language, and it has hundreds of thousands of users, but not hundreds of millions of users. So it's a completely different kind of scale than Microsoft's product languages. Whether it will ever become a language on that scale, I don't know. And it's always I wouldn't want to give up being an ideas factory in order to get that. I'd rather, I'm just delighted that my colleague Don Syme, who is 3 doors down the corridor has developed F#, in which it now acts as a kind of pipeline. So now I can get pipeline ideas out of Haskell into F# and out of F# into C#. And I'm also delighted that he successfully made the case to Microsoft to turn it into a product that the company does support in a way that Erlang is supported and Haskell is not. So F# really is a Microsoft product. That's a huge breakthrough for a big mainstream company like Microsoft to support a functional language. But the ideas factory is the bit that I say is the most important thing, the high order bit.
Yeah, that's fun, isn't it? Yeah. I mean, it's the same in Erlang. I mean, I think in a way, you're graphing it, said you have this initial enthusiasm, you go up to that, and then there's a sort of plateau where not much happens.
Yes.
I think that happened. That happened in Erlang as well. Like, you don't things, which I don't understand why, seem to be very stop-go. You know, you work on things and suddenly there's something happens, a lot happens,
yes.
and then I think is it a time taken to ingest the ideas, where it's just sort of these ideas are sort of fermenting in people's brains for a long time, and then they sort of and I think true concurrency, true things when people started being permanently connected to the internet with broadband connections, that's a kind of quantitative change, and you saw the file sharing networks, you saw all these things. So it's only about 4 or 5 years ago that people started deploying distributed algorithms, and the first few years of that, they said, well, what should we do? Well, nobody knows, so they invented BitTorrent and things like that. You have social networking programs, you have things like that. Google Wave will sort of come along and replace email in a few years' time or something. And so suddenly people want to know how to write distributed programs, which they never wanted to do before. So how do you do sort of distributed transactions and things? How do you do consistency and things like that? So what was a pretty obscure part of computer science is distributed algorithms. And then he said, well, we've got these to do. How the heck do we program these things? Well, in Erlang or Haskell, these algorithms are just difficult. But in other languages, they are
downright impossible.
Yeah, right. I mean, even if you have a very clean, pure programming language, and you take sort of Paxton algorithms or something like that, they're complicated things. They make your head hurt. And there's a whole sort of branch of mathematics, a whole branch of computer science who understand distributed algorithms, and they live at the bottom of these social networks and things, ticking along. So I don't think you're going to see Erlang sort of replacing JavaScript or anything like that in browsers, but you might, where you are seeing them are being deployed in the infrastructures, in the clouds and things like that, to glue the bits together properly, because that's where you need the complex algorithms. So we're seeing a sort of infrastructure building things, cloud computing, and sort of what are you doing inside massive multi-cores? How do you organise computations? That's where we're being used a lot.
Whenever you've got concurrency and multiple processes working, you need to be very careful about effects, side effects.
Sure.
And otherwise you'll just does your head in. Yeah. And so something that Haskell and Erlang both share is being careful about effects. Now Haskell is sort of super careful and Erlang is merely careful. But they're in both cases, you don't have this unrestricted side effects all the time, the computational fabric being effectful, that it seems to me makes it really it makes it jolly hard to write programs that exploit multi-cores.
I wrote some... I didn't really know what thread safety was in Java, so I wrote a little Java swing thing, and a Java friend who I asked. I wrote this little Java process, and it worked fine. I could create one window, and then I created 2 windows of graphics program, and then I sort of drew a rectangle in one, and I drew a rectangle, and it crashed.
Oh.
And I said, well, why did it crash? And he said, well, it's not threads, the swing library's not thread safe. Said, what's that mean? Well, it means if you've got one thing that works, you do 2 of them in parallel, they sort of interact in strange ways. And I thought, how can you program like that? It's impossible to program.
Somehow so state.
It's just, it's kind of, if you've got this non-thread safety, maybe you've got this code that's thread safe that reads stuff, and this code that's thread safe and writes stuff. You try and compose it into a program that reads and writes, and it wouldn't work. And then you're kind of scratching your head and thinking maybe something's wrong. Oh, let's put a mutex or a lock around the whole thing, and it works for a while, but somebody else has forgotten to lock it. Or what happens when it crashes? I mean, how is the failure model integrated with the locking models and things? Because if you lock stuff, it assumes you don't fail, and you can release the lock, and it getting very, very... And then you hide that in a library so nobody can see and sort of inherit stuff from it, and you've got a mess.
One of the ways that I speculate that functional languages may end up influencing the mainstream is by that mainstream languages will gain a larger and larger subset of purely functional programming that will make it easier to write functional programs that don't use side effects a lot. So you can get more and more computation done, useful and complicated computation, like the algorithms you were describing, without using side effects. And I think that'll, as they get richer subsets, F# is an example of this, because it's built on a substrate that is completely imperative, right? The .NET system is an imperative system, but F# makes it easy. It reduces the barrier to entry for writing functionally. And I think that's a trend that we'll see continue.
Yeah. I think what I noticed is that the Erlang libraries are pure libraries, and the pure functions are incredibly reusable.
Yeah.
They just work forever. You do them, you test them, and you forget about them. And you can reuse them in many different contexts that you hadn't thought about. And so the goal in system design is to divide your system in such a way that as much as possible of it is pure, and the messy stuff's on the side.
That's why you need those types, Joe. To tell you
that's why you do. No, that's why you need that's why you need good error recovery mechanisms. Because even with your types, you'll need to test it. I mean, come on. First I want to write a factorial program. My factorial program will say factorial of n is 42, and the type inference name will say this is a type int to int, and so it's okay, so it's correct. So you have to give it. You have to say that factorial 3 is 6.
You're misrepresenting me, right? I never said that types guarantee your program is correct, but you were talking about segregating effects. And types are a very good way to segregate things.
So in the same topic, actually, in Scala, which we say that get inspired from Erlang for the actor model, they don't copy memory. They don't copy the data structure, but they rather share them, and there are no constraints on the data structure. So it's not. It could be mutable and it could be shared. And Martin Odersky, father of Scala, he wrote a paper about using types, be it inferred or not, type annotations for guaranteeing that the reference is not consumed by concurrently. So, you can use mutable data structure, which is very, very nice for performance reason. Yet, you get some guarantees of not having race conditions. Can you talk a bit about that from the two perspectives?
Well, so the first thing to say, Scala is not just a knockoff of Erlang at all. It's a whole sophisticated language with that kind of rather elegantly combines functional and object-oriented systems in a rather innovative and unusual way. So, I think you're right that one thing you can do with Scala is implement an Erlang-like model. So then, once you've got an imperative system in which you can mutate things, it is possible to use type systems to kind of constrain exactly how you mutate them, so that, for example, ownership types in object-oriented languages are an example of doing this. I don't know about Scala's. I don't know the paper that you're describing of Martin's, but the systems that allow mutable objects to flow around and be used once and be owned by different threads can work, but they tend to be rather complicated. And my gut feel is that you need type systems that are tread this narrow line between being expressive enough to say what you want and not being so complicated that nobody can understand them anymore. So, and I would think rather than having let me put it like this: ownership types for a conventional object-oriented language are a way of controlling some of these things, but that feels to me like taking a system that's already using too many effects and trying to retrospectively patch it up. It's better to start, from my preferences, would be to start with a system in which effects are A, few, because the functional subset is very big, and B, rather constrained. And now Haskell has a rather crude distinction between effectful programs and not. That's not enough, right? To just say it has some effects might not be enough. So that gets you back into the land of controlling effects more precisely. But at least it's a smaller piece of your program. At the moment, I'm agnostic about whether types are the right mechanism for trying to do this much more fine-grained control of effects, in which you're saying this reference is owned by that thread for this period, and then the ownership moves to that. That's a rather sophisticated thing to do. Very clever. Very interesting papers written about it.
I don't like the idea of mixing things too much. So,
what sort of mix?
Well, if you look at Haskell, Erlang, Scala, and F#, right? So what you see, if you look at Haskell, you see something which, within its context, within the little framework it sets up with Sandbox, is very consistent, very beautiful. If you look at Erlang, it kind of the bits fit together nicely. Of course, they don't fit together nicely with the JVM or with .NET or anything like that. So if you want to use all the nice things that are there, you can't use them. Or you can use them, but it's difficult. So the other approach is you say, well, let's use the JVM and target lots of different languages so that the different languages can use each other. Or you can do that within the .NET framework. So you get Scala and you get F#. And so the benefit there is you can use all these other things that are available. But in order to do them, you have to massively corrupt and break these abstraction boundaries. So that and I don't like that. I think you're breaking abstraction boundaries in the wrong place. So how I would like to see systems built is through communicating black boxes, and I would like to see the type systems applied to the definition of the protocols themselves, and I haven't seen that done.
Oh, there's been lots of work on that kind of stuff in the type system for contracts. They're also
But yes, I've done some stuff myself, but I mean it seems to have very little impact on how protocols are designed. I mean, protocols are designed typical ways. You write RFCs and things like that, and they're defined in English with text. And a lot of people think they're defining protocols. They're in fact defining message structures, and they don't say anything about ordering.
You must send an A and then a B, and there must be a reply.
And APIs to programming languages don't. If you look at sort of classically, an API for a file might say you can open a file and you can close a file and you can read a file and you can write it. They don't tell you that you have to open it before you can read it, do they?
But that's another thing to do with state, isn't it? The very idea that there's a thing that you do things to is part of what gives rise to that problem.
So a lot of programming languages, if you have a file open and read and write, the program is supposed to know just by magic that you should open it before you read it. What's that mean in a... Okay, so that makes sense on one processor. What's it mean on a sort of parallel program? You've got lots of parallel things, and that one's opened it, and that one hasn't, and is it open? What happens when you have two things that try to open a file at the same time, and do you get sort of two copies, and one of them fails? Is it like a transaction? Is the file put back to the old? Then you start trying to read the APIs. You can't find the answer in the API. So John Hughes was saying, did you know that if you open a file and write it and rewind it and do this, then this happens, which is very counterintuitive. And you try and look in the POSIX specs, and you can't find any reference to what this should do. And his quick check program discovers things like this. So I think, if you're doing I/O properly, in the sense that you do it, you don't do it at all and save it all up to the end, then do it. A lot of those problems go away.
Yes, we don't actually.
Well, that's what you say you do.
It just looks like it. We certainly don't save it all up to the end.
What, you're fibbing?
So it was a short talk, right?
It says in the books as well.
No, it's not. No, read Tackling the Awkward Squad. There's a very detailed operational semantics given that explains that I/O happens as you go. Right? It's no good if you want to. So you've got to print the message and then read the response and then print something else. You can't save that up to the end.
No.
Yeah, but that takes us to a discussion about user model, because for me as a user, for example, of Haskell, I have a mental model that everything is happening by the end, right? That's what the type system tells me, that everything is saved until the end.
Oh, when you mean a user model, you mean the programmer?
Yeah, I mean as a user. Yeah,
not the user.
Yeah, no, the user.
Yeah.
Okay. This is in sync with how things happen, but sometimes it gets out of sync. It's the same thing with when you're dealing with processors, right? Because you're sending messages, but sometimes it's maybe not that cheap to send a message, and also it gets like barriers of using this mental model that you established. So what do you think of this problem?
I don't think I understood the question.
Okay. So with any feature of the language, you define a kind of mental model for the programmer, so that the programmer can reason about this feature. And the implementation tries to get in sync with this mental model.
To be faithful to it.
Yeah, exactly. But it's not always true. In some cases, it gets far from it. It's the same thing with processes. When you are sending messages, sometimes it's not exactly the same thing, because you need to copy, or you don't need to copy. Sometimes it's not performant to do it that way. You do it another way. So what do you think of this problem? The same thing with the I/O. That as a programmer, I think that it's happening by the end, but it actually is happening on the fly. It's happening right away.
So it is happening right away and by design. So I think the presentation that I gave today, which said the main program is an I/O action, which is gotten by stitching together other things, is that's a first approximation. So I've taken quite a lot of trouble actually to write a tutorial that explains in rather more explicit detail. I mean, that model doesn't work at all for concurrent program, for example, where you're spawning threads that have got to talk to each other. Of course, you can't save all that up to the end. So no. The I/O monad is something that is an action that runs in an interactive fashion with other I/O threads that are going on at the same time, and it's possible to give a much more precise model for what's happening than, say, you save up one big thing that's performed at the end. So I think the truth would then be the one big thing you do at the end is just an oversimplification that you might do for your first program that just printed 3 things, but then you have to get a slightly more sophisticated understanding of what's going on, or alternatively just bail out into well, it looks like a C program and actually it runs like a C program. You say do print this, read that, send this message to this other process, and that's exactly what happens, just as if it were a C program. So is it where you can look at a monadic I/O Haskell program through 2 sets of spectacles. You can either think of it very much like an imperative program, and that's a very accurate model actually, or you can think of it as the compiler does, in this more functional way, and that's what means that the compiler's optimizations are actually robust. So I suppose that's the way I deal with the dissonance, is to try to say that was an oversimplification to start with.
Yeah, well, you don't tell all the truth.
That's right. You tell the truth in bits.
For example, it might sound that when you send messages between Erlang processes, your mental model of what's happening is you copy everything.
That's right.
And indeed we do copy everything. Apart from, now as a small print,
yes.
if it's a big binary,
yes,
and you're on the same processor, then it's in a shared heap with a reference counting garbage
and it's immutable,
yes,
of course.
Yes. And but it's like what's it called in operating system? When you have a process, if you don't write to the memory,
right.
You've got the same memory, but you do copy on write. So when you write to the memory, you split it into 2. So the binaries behave like that, and they're in a shared heap.
So you do have to be a bit careful about your cross model. If somebody
depends,
redistributed that, so suddenly it was on a different processor.
No. But if you distribute it, then it is copied. Okay, because
that's what I mean. So suddenly the program would run at a very different speed.
Yeah. And then it's not
and
even that statement.
That.
I mean, yeah. So yes. So, but even that statement that it's on a shared heap and binaries are not copied is not true for small binaries, because small binaries are copied, because it's just not worth sharing them and doing things. And even that statement's not quite true, because sometimes you keep fragmented ones and do so. There's an awful lot of small print.
Well, it's the business of a runtime system, provide a simple abstraction for complicated
should a
stuff.
Should a programmer need to know about that stuff? No.
No. Well, but you're talking about the cost model,
yes,
right? Whereas you were talking about the understanding what semantics of the program is.
Yeah.
So I think
semantics. But when performance is a question, you need to think about performance, right?
Yeah.
So in the same sense, like how much the programmer should know about what's actually happening with processors or processes. Like what we saw in your presentation is that you started with a quite transparent system, or a system that where the programmer doesn't know on which thread things are executing, and you ended up with something very explicit, right? Saying your processor, you executed this, the other processor, you executed something that's similar to Erlang. So where you think,
I think when you say the programmer needs to think about performance, you need to I wouldn't say that the programmer needs to measure the performance of the programmers, because the one area where my intuition is really wrong is in guessing. It's about guessing performance. Apart from the fact I know the input parsing stuff is usually the big bottleneck, but apart from that, and when you put these, when you have virtual machines running on top of multi-cores with core affinities, and you put virtual machines inside the virtual machines, and your intuition about performance goes out of the window.
Yeah, but sometimes you give some hints to the compiler, in a sense like this is a feature, or this is a delay, or whatever it is, and sometimes you're really explicit. You say, I need a process to execute this. Or the same thing with data parallelism. I say I want this list to be executed in several processors. So I'm very explicit about
I
this.
mean, I think annotating your program with parallel things is very, very difficult. Your intuition will probably be wrong.
Yeah. So you need, and what you're saying is you need good profiling tools. Because your own intuition about how sequential programs run is often wrong too. Yeah. And it's silly to spend time optimizing code that isn't going to run very much. So you need good profiling tools. And one of the things that GHC, our compiler, has not been good at until really quite recently is having good profiling tools for parallel programs. Right? Because you really want to know, why isn't it concurrent? Or maybe it is concurrent, the granularity is too small. Oh, so why? So you need good insight into what's going on. That's quite hard to do. So my colleagues Satnam Singh and Simon Marlowe are working on a device called ThreadScope to, for the first time, give some insight into that. Lots of other people have built profiling systems for parallel systems, but we've been lagging a bit there, really.
So the interesting question is, in Erlang, I mean, everything is parallel because we start off with loads of processes.
Do you have profiling tools?
Yeah, sure.
Yeah, so
yes, absolutely.
Yeah, so you can see, this process is stalled, and this one is maxed out.
What's interesting then is finding the sequentiality. Sometimes the system just degenerates to one sequential process, and you think, why?
They're all waiting for him.
Yeah, what's gone wrong here?
Yes.
And that goes back to algorithms, because a lot of the sequentialities in this one place where you have to do allocation. So if you've got a booking seats for an aircraft or something, you could have one allocator. But if you wanted to parallelize that, then maybe you've got two allocators, and you have all the odd seats, and you allocate all the even seats. The problem there, you can't sit next to your wife or something, or you might give half the seats to one guy and another, and maybe you want better than that, so you split it into four. So probably you end up with a sort of logarithmic allocator that's kind of message passing and things to get rid of these bottlenecks.
Yeah.
And
you've got to know that they're there in the first place. That's what you need a good profiling for.
Yes.
I think okay.
But I think, I think the things you see in clusters, in a cluster you have variable latency and you have load balancing and things like that. So I think you're going to have to put those in the Erlang runtime system and sort of hide them under the counter and do exactly the same thing that people have done in clusters for years. To make, because a big multi-core is a cluster and it's on a chip, and the latencies are different. The different cores have different caches, so you can send messages between two cores very quickly and between two other cores very slowly because of the memory cache architecture. And I think that needs to be reflected in internal load balancing and all sorts of things. But the programmer shouldn't see that.
And they're not new problems, right? People have been working on them for quite a long time. But I think the differences in languages like Haskell and Erlang is that the programming abstractions are rather higher level. And the higher level programming abstractions is good for the programmer, because it means they don't have to worry about things. But it means that the runtime system and so forth has to cross a bigger abstraction gap. Yeah. So the programmer, in effect, has less control. The more control the programmer is prepared to take, then everything becomes easier. Not only does the programmer make better decisions, perhaps, at the cost, perhaps, of a lot of work, but also if you do have profiling tools at a lower level, then those things are easier to measure and present to the programmer. At a high level, it's quite hard to think what to measure or how to present it. So I think we're still finding out how to cross that abstraction barrier well.
And each new generation of chips is... We don't know. We're doing experiments. We don't know what's going to happen.
New layers of abstraction within the hardware, as well. Yeah. So you have much less control than you think, really.
So it's actually...
It's amazing the thing stuff...
I mean, it's quite fun, because we've got these new Nehalem processors and boards and things, and I don't know what's going to happen. Make measurements. I don't know.
Yeah.
I mean, I think it's rather exciting now, because we've gone through, the last 10 years... I knew what was going to happen, more or less, so I could predict. And then the big multi-cores start coming out, and the Tylera chips and things like that. And what's going to happen? I don't know. It's back to experimentation. Look at the Intel Polaris chip.
Some of it's a bit tiresome, though. These
gigaflop at 11 watts or whatever it was doing.
Because these machines... these machines have lots of layers of abstraction in them, and they're all not quite under your control. So you can spend a lot of time measuring things, and sometimes it goes faster and sometimes it doesn't. Or you might discover that the reason it's going slowly is because two unrelated variables happen to be allocated in a place that was in an adjacent, the same cache line. There are better things to do with your life than figure out the two variables. That kind of work doesn't feel productive to me. But the more sophisticated the underlying hardware gets, the more you have to do that. So I don't quite know what to do about that, except build systems in which that have some kind of built-in locality. That's the data parallelism stuff I was talking about. That's my best hope for dealing with these very these machines with very non-uniform memory access.
Yes, I think in Erlang we might start migrating processes. Find that these two processes are talking to each other a lot. You just sort of migrate them.
Oh, well, Joe, that would be lovely.
Put them in the same core.
Difficult to do.
No.
We
have our own stacks and heaps.
Oh, yeah, but no, when I say it's difficult to do, it's difficult to do well. So we have our own stacks and heaps, of course, so we can move things about very freely. But then we find the reason the thing's going so slowly is because this process keeps migrating around. It's never in the right place. It keeps migrating to where it thinks it's meant to be, but actually it turns out it's always in the wrong place. It's really annoying when that happens, and it always happens on the test program that the first student writes. Real systems, it's often more okay. It's like factorial. They write factorial, doesn't perform well. So I've told you what I most envy about Erlang. What do you most envy about Haskell?
Oh, the types.
Aha! That was a short answer.
No, I mean,
they're
very nice. I wish we had.
Yeah, but then
on the other hand,
lose stuff
don't
too,
you?
See?
Okay, Michael, don't you? Wouldn't you love to have all these generic term to binary and all these sort of things? How can you live without them?
I have a little bit of residual envy about generic.
I mean, you could just take anything and compare it and just serialise and just send it anywhere.
Oh, it's sinfully easy.
And the garbage collector doesn't need to know about what types it's generated. The
garbage collection, that's not a problem.
Tiny little thing.
No, our garbage collection our garbage collector is complicated not because of types. It knows nothing of types.
Oh, okay.
So garbage collector is fine, but I have to admit, for just walking over trees of arbitrary size generic programming, lack of types is very convenient.
Wouldn't you like that? Wouldn't you like some dynamic?
But haven't you enjoyed the whole cottage industry of papers about typed generic programming, which has been extraordinarily creative? People have done extremely clever things. So that would never have happened. It's like necessity is the mother of invention.
I read the Real World Haskell.
Yes,
and
yes.
It's very nice. I really. And the Erlang book's coming out, and when I was reading the Real World Haskell, I started off reading the simple programs. They were obvious. The more complicated programs, I was writing the Erlang program in the margin next to it to understand it. And at that point, I was struck by how similar they are.
Yeah.
The other thing is, you talk about the first thing Haskell programmers do is write down all the types, and they're doing the design. Well, that's exactly the first thing I do. In my head,
right?
Right. I write the odd comment now and then.
So I just want you to have a way to do that.
Don't you miss now? So when you're developing Erlang, you don't have to write the entire program and get it to work. So you're not quite sure what the types are. Okay, so in Erlang, you just write some program here, and you evaluate something, and it throws out this great big thing, and you say, oh, that's what the type was, and now, and then you can say, well, that wasn't quite right, so I'll change it to that. But you're not restricted in having to get all the bits working before you can just do those experiments. Oh. Wouldn't you miss something like that?
No, you still don't have to get all the bits working.
No.
But you have to think what type it might have, but you might evolve that type.
But in Erlang, you can just run it and see. So, for example, if you're doing somebody wants to use some we have things called parse transforms which allow you to change the in a module. You can say there's a parse transform, and the parse transform is given the parse tree of the program, and it can turn it into another parse tree before it's given to the compiler.
Right.
So that's a way of doing deeply sinful things which you normally can't do. And the nice thing about that is somebody was asking, well, how do I get started with this? Well, there's a function, EPP parse form, which just takes an Erlang module and it produces all the abstract forms in it, and then you dump it into a file, you see. And then you just open it up in a text editor, and you don't need to know anything about the types. You just read it. It's pretty obvious. I think it says this is a function, and you can sort of guess what the stuff does.
You're looking at the parse tree of a particular Erlang program now.
Of a module.
Okay,
yes. And it's because it's got this generic sort of structure, and you just dump it all out, and then you look at it. You don't really need to know what the types are, and you can guess, well, I can see that's a function application, so I can start transforming it. You write generic functions that just walk down the whole parse tree and extract all the variables from it without knowing what form of tree it is. Tiny little functions. You miss things like
that. I don't think I do, actually. So
actually, we're biased.
Exploratory programming, right? I like exploratory programming.
We should ask John Hughes or Simon Thompson, who have more experience of both worlds.
So John has promised me a paper on why static typing is harmful. So because he's somebody who sort of grew up with static types, but he's done a lot of Erlang programming now. So he has quite a visceral understanding of both,
right,
and he's told me that he'll write a paper about this.
To me, good functional programmers who come to Erlang, both Phil Wadler and John Hughes, when they came to Erlang, wrote the most bizarre Erlang programs I've never seen. For the first thing they do is they define a macro, which is freeze.
Which is what?
I think they force or freeze or something, which makes it lazy because it just returns the fun, and they are forced to evaluate it.
Okay, right.
And then they write their entire program, which looks to be, from an Erlang point of view, like a Klein bottle. The entire program is inside out, and it just ends with a sort of force of freeze of. And they write completely incomprehensible Erlang code. It all works beautifully, but it's...
I don't think it has anything to do with types, though.
No, it's to do with lazy evaluation.
Yes,
That's forced them to
yes.
think in a different way.
You want to write lazy Erlang programs.
Yeah,
they do.
Yes, they do.
Yeah.
That's the first thing they do.
Oh, well.
And it makes them...
There.
It's really weird, Erlang.
So if you're going to write a lazy program, you probably wouldn't choose Erlang as your first language. But I think, going back to what you're saying, when you start thinking about your Erlang program, you do think types in your head.
Yes.
So the ability to write them down in a formal way and have them checked,
That's good.
perhaps
That's
while
good.
not
Yes.
denying an exploratory
But
program.
I'd like the other
would be
stuff
good.
as well.
But in fact, several people, more than one person, like Phil in the first place, and Costis or some of his colleagues have designed soft type systems for
Yeah.
Erlang.
Yes. Oh, yes.
But they never really caught on, and I'm never quite sure why.
Well, they've got the dialyzer. We run that. With
You do use it on a regular basis,
absolutely,
do you?
yeah.
Oh, right.
We sort of, especially in big projects. I mean, it's in part of the. We have automatic testing, and we run through these, and we look through. But they actually, by the time they've been through the test suite, it picks up very few.
But you're using
errors.
it as an error checker rather than a design tool. I mean, you don't use it to write
yes.
down your types, is what I mean. You don't use it as part of your design flow.
No, we don't.
Whereas I think that's probably the most powerful thing about types is to use it as a design tool.
No, I think we should have gone down type checking rather than type inference, where we start by writing the type signatures and then type check rather than just inferring what we've got.
Now, you're saying that writing a type doesn't mean that the program's correct, but in some ways, for me, that's the whole point, right? That a type is a weak specification.
Yeah.
It's a partial specification, which means that it can be small. So I can say in one line something that is meaningful to me as a programmer and that helps me glue my program together without having to specify lots of details about exactly what it does. You know, it's called lookup, so I know what it does, more or less, right? And then its type tells me a lot more detail.
But I must admit to a secret, sort of, when I'm thinking about a program, you hold these inner mental dialogues before you write the program.
Yes.
And my mental dialogue is, suppose I'm writing a blog software, sort of. I said a blog is a sequence of chunks, and a chunk is a title or a paragraph, and a paragraph is a something or a something. You know, and I'm sort of very strictly having this little dialogue.
So secretly, you're writing a Haskell program in your head, but it comes out in Erlang. Yes?
No, and then I type it in, and of course. And actually, for difficult problems, I actually sort of write this down in English or in an informal notation. So I'm not saying that. No, they're good things.
Thank you, Simon and Joe, for being here for the interview.
Thank you.
Fun.